Next, we are going to have Clipper, which is a low latency prediction serving system that decouples applications from models. Simon Mu, he's going to present and lead the tutorial. He's an undergrad that has been doing great work with us in the RISE lab.
Hi, I'm Simon. I'm one of the lead developer and maintainer of the Clipper project, and I'm a student researcher at RISE lab. So Clipper is a team effort. Today I'm representing my whole team to tell you more about Clipper and prediction serving today. So in this RISE camp, you'll learn more about the machine learning lifecycle, the procedure it takes to develop a machine learning application. So it has 3 stages. It has model development, model training, and inference. Today, we'll be focusing on the inference stage, where we take trained model, expose it as a prediction service, and then interact the prediction so the prediction service can interact with end user applications. In particular, these inference stage need to serve prediction for large-scale interactive applications. The prediction serving has unique requirements. It needs to be fast and scalable, so it can maintain low and predictable latency for large-scale interactive applications. So for latencies, we're talking about tens of milliseconds right here. And it needs to be manageable, so engineers and data scientists will find it simple to deploy and monitor. And we also need to support a wide range of machine learning frameworks. Finally, it needs to be affordable, so we can minimize compute cost. For example, many machine learning models run on expensive hardware like GPUs. So in this talk today, I'll tell you about what prediction serving looks like in industry today. I'll tell you about Clipper and its architecture, and finally, I'll give you an update on the project status. So prediction serving today can be divided into 2 major approaches. One is what we call pre-materialized predictions. The other is called put model in container approach. Let's take a look at the first one. So for pre-materialized predictions, after the training stage, when we have trained models, what we will do is collect all possible queries and then score it with the batch training framework, the same framework we use for training models. And then the prediction will be stored in some data management system like a database. What's important about here is all these steps can be accomplished using standard data engineering tools. And then at serving time, the user-facing application will directly query the database, and then will return the decision. So now has transformed a low latency prediction serving problem into a low latency data serving problem, which is a well-studied problem, and there are a lot of industry-grade, enterprise-grade solutions out there. So we can serve with low latency with little effort. This approach is simple to deploy with standard tools. It will be low latency at serving time. However, one of the major disadvantages is that it requires full set of query ahead of time. This is fine if you have small and bounded input domains. However, if your application requires, for example, a user to upload images at serving time, there's nothing this approach can do about it. In addition, this requires substantial computation space because we need to score all possible contents. And finally, it will be very costly to update because once your data scientist updates the model, for example, give a new version of the model, you need to rescore everything, and that will take hours. An alternative approach is what we call put model in container approach. So if we take a step back, think about how do we deal with packaging predictions, we're exposing the model as some service. So we need to package the model in some prediction service. And Docker container is a great technology for that. So just to get everyone on the same page, Docker container is this technology that will package up code and all its dependencies. And so application can run quickly and reliably across different computing environments. You can think of it like a lightweight virtual machines. So how do people actually do that? After the training stage, when we have the trained models, So data scientists or engineers will write the Docker file to package all possible dependency, package the model into the container, and then they will build a web server wrapping the model. And then they will possibly add logging and monitoring and metric support. And after you build everything yourself, this Docker container can interact with the user application directly and will render the prediction. So this approach is general purpose because you can package everything into the Docker container, and it will also render prediction at serving time. However, one of the major problems is that it requires data scientists to write performance-sensitive serving code. And it is also inefficient use of resource because we use throughput-optimized framework to render prediction, a single prediction at a time. Finally, you have minimal support for monitoring and debugging. So for prediction serving today, how is it practiced today? We see that pre-materialized prediction does not meet our requirements because it does not render prediction at serving time. We see the modeling and container approach does not meet the requirement because it requires data scientists to write performance-sensitive code. So current approach do not meet the requirement for prediction serving system. Can we design a system that does meet those requirements? If we take a step back, looking at the situation right now, we have a wide range of frameworks that's used to train models, and we're using these models to serve a wide range of applications. We need to have a general purpose system to decouple model and application. We need a common middle layer to embrace the heterogeneity in both application side and model side. So with this middle layer, we can have both the application and model to develop independently. So what Clipper does is we interpose this middle layer, and that provide common abstraction that enable us to build general purpose system. And behind the common abstraction, we added system optimization to make it fast, scalable, and affordable. So the design of Clipper really falls out from the desire for a general purpose system. It sits above the container to decouple application from specific model instances, and we act as a single general purpose system to serve a wide range of framework and application. You can really see that we actually, what we're doing here is we're extending the modeling and container approach to design a prediction serving system that will meet the requirement to be fast, scalable, manageable, and affordable. Now I'll talk about the design of Clipper and how do we achieve each of those requirements. So Clipper is a distributed system. At its core, it has a query processor interact with the user-facing application. And then the query processor will take the query from the application and route it to corresponding model container. We have a slim management core with configuration database. And user will interact with our management core with a Python API. We also have the monitoring support so that will gather all possible metrics. In addition, we also run Kubernetes alongside with your other microservices. So now I'll give you an overview of what does the life of query in Clipper look like. For example, right here, we have two models. And for these two models, Clipper will have model queues for them inside the system. And now the first application generated a query. The query will be sent to corresponding model queue, and it will be collected with other query that's inside, that's sent before or after within the same time frame. And then Clipper will handle them as a batch, and then we'll send it to the model container. We'll render the prediction using the same original framework and the same code, and then we'll dispatch the prediction back to the application. Now, I'll start talking about how does Clipper meet the prediction serving requirement we laid out today. So to make it manageable, Clipper employ simplified model deployments. We also add support for custom model metrics. So what Clipper does is we encapsulate a model behind a uniform interface so we can evaluate a model using the original code and system. We abstract away performance-sensitive serving code from data scientists. In addition, because each model is running in its own Docker container, if one model crashed, it won't bring down the whole system. So what does this actually look like? So what the data scientists need to do is implement this model container API that takes some model data, initialize the model, and handle a batch of input at a time. We have API support for many different languages, including Python, C, C++, and R. On top of that, you'll package the dependency, for example, the model implementation, as well as always module dependency into a Docker container. However, there are many data scientists who do not have experience with Docker, and one of the goals behind Clipper is to make it easy for data scientists to deploy models. To do that, we develop a library of model deployers. These model deployers help data scientists to deploy a model directly from the training process without knowing anything about Docker. So for example, right here, we have data scientists interact with Spark cluster inside a Jupyter notebook. And then the data scientists develop a Spark machine learning model. And then the data scientists just need to call Clipper with one library call. Clipper will automatically and intelligently save the Spark context and package all its dependency, including the model, into a Docker container and connect that with Clipper. We provide a library of model deployers that automatically and intelligently save all prediction code that capture both framework-specific model and arbitrary serializable code. Such that we can replicate training environment and those prediction code in a Clipper model container. We've provided a growing library of these deployers in Python, including the popular machine learning framework like scikit-learn, PySpark, TensorFlow, and PyTorch, and many others. We also support serializing arbitrary R function and serve arbitrary R functions. However, just put your model out there and running is not enough. A data scientist or a team need to figure out how the model is doing as it's serving live traffic. So to do that, Clipper let data scientists to export custom metrics for every model they deploy. So while you're writing the prediction code, you can register and report metrics directly from the model containers. And these metrics is available with model deployer as well as the custom containers. And then the results will be exported to Prometheus along with other Clipper internal performance metrics. So these model metrics enable users to track both physical and statistical performance of model, and it help you detect and diagnose model degradation. For example, when do you retrain the model if the model is behaving not as expected? And it will also help you debug physical and statistical performance issue. Now, having addressed how Clipper make prediction serving manageable, I'll talk about how Clipper make prediction serving fast and scalable. To do that, we implemented hierarchical scale on Kubernetes, as well as some system optimizations. Let's talk about the first point today. So to do that, sometimes a single model does not handle the load of your traffic. Clipper allows you to replicate model directly inside Clipper. And if a single Clipper instance is not enough, or you need it for fault tolerance reason, you can directly replicate Clipper as well. So hierarchical scale enables fine-grained replication to minimize cost while scaling to massive workload. Finally, I'll talk about how Clipper make prediction serving affordable. In addition to hierarchical fine-grained scale-out, we implemented something we call latency-aware batching. So one important observation is that batching improves resource utilization. For example, a single page load may generate many queries, and you have many users that generate these queries. And then these machine learning frameworks are throughput optimized because they're used for training. And this throughput optimized framework will take advantage of data parallelism in the both software and hardware. So we can handle a large batch and have maximized the throughput. However, just increase batch size is not enough, because as you increase batch size, of course, the throughput will increase. However, the latency will increase as well. So finding the optimal batch is tricky. It depends on hardware configuration, model and framework, system node, and latency budget. So in order to be latency aware, what Clipper does is to adaptively trade off latency and throughput. We'll have an explore stage where we increment batch size until the latency objective is exceeded, and we'll have exploit stage where we use this latency measurement from the previous batches to estimate the optimal batch size for the particular SLO constraint and for that model. So we just talked about how Clipper is this middle layer for prediction serving that have common abstraction to make it manageable, have system optimization to make Clipper fast, scalable, and affordable. So what's the current project status for Clipper? Clipper interposes as this middle layer, and at its core, we're only about 10,000 lines of C++ and 8,000 lines of Python. We're open source under Apache license, and we're designed to support production-level query traffic. We released 0.03 in June. This release includes metric and monitoring infrastructure using Prometheus, includes support for user-defined metrics, we just talked about. We support hierarchical fine-grained replication, as well as we add a new latency-aware batching algorithm that use less resource as a previous iteration. And also added several new model deployers. As for community and adoptions, we're working with initial users to deploy Clipper in production. This includes ARM online. And as for the status of the community, we have about 29 contributors right now, and many of them are from industry. We're looking for new contributors, and we welcome many new feature requests. And to get started with Clipper is very simple, because Clipper is a fully distributed Dockerized system. All Docker images are available publicly on Docker Hub. And to really get started with Clipper, you just need to have an environment like Docker or Kubernetes, and then you just pip install without cloning or compiling at all. Now, I'll talk about what's next for Clipper. We'll want to explore how do you compose model together, how do you deploy and provision a multi-model inference pipeline. We're investigating this in the Inferline research project. If you're interested in the model composition work, you can talk to me or Alexei on the back later today. And we also want to explore model selection policy, like label-based routing, A/B testing, or smoke testing. Finally, we want to explore how to do auto-scaling with models. How do we scale model up and down to handle spike traffic, as well as to reduce cost? So tutorial today will have two parts. Part one will give you an overview of the API, your experiments with Clipper with its model version management, as well as hierarchical scaling ability. In part two, you'll deploy some example applications, including an image classifier and object detection model. You can do them in either order, but we recommend starting with part one. In summary, Clipper makes prediction serving simple and easy. You can go to clipper.ai to check it out. And now I'll take questions. Thank you. Yeah. Question? Sorry, is there a mic again? RPC. So for the user-facing side, we use just HTTP and JSON because we're designed to directly interact with the end users. And interacting with a model container, we have our custom RPC using 0MQ, so that's pretty efficient to send large batch of data to our model container. Pardon me, I really couldn't hear. So our Spark container is actually using PySpark. So we have our RPC layer is in Python, and then we'll use the 0MQ and pass it through PySpark.
But Python, no, I mean Spark itself, it has a batch system. So every time you starting the batch from the beginning, or because you were saying you only have 10 milliseconds latency.
We're designed to support tens of millisecond latency. Yes.
Okay.
Yeah.
So it's not for Spark yet.
Yeah. We do support PySpark model though.
But how can you get PySpark model? Because when you run PySpark model.
Yeah, it is possible it has higher latency requirements. It could be, it might be slower, yes.
Got it. Okay.
Thank you.